Now that we've seen several related rates problems, it's worth teasing out some of the common threads that we've seen. First element for all of these questions, any word problem if you can, is to draw a picture if at all possible. And just as important, label the variables that you're going to use. It's so critical that we distinguish between dx dt or dy dx or whatever derivatives we're looking at. We have to know which variables are which in our scenario. It's not one of these places where we can play a little fast and loose with x being the default. We have to have these variables labeled and clearly defined, and it's easiest in context with a diagram. Then we simply look at, from those diagrams, which things do we know, which things are we trying to find. Those are the classic mathematical problem-solving goals. And write an equation involving the variables, and the key thing is here, no rates to start. We're not looking for the derivatives at the outset. They come later on in the process. In fact, they come at the next stage when we apply implicit differentiation to the equation before we substitute any known variable values. Then we plug in some individual things. Usually it's phrased as when t equals something or when x equals something. Then that gives us enough information to solve for the rate we're interested in. If you look back at our earlier examples, you'll see those themes, and we're going to try to bring those out clearly in the example we're about to go through as well. The example here is going to be a classic of calculus classes around the world, and that's going to be a problem with a ladder. So imagine a ladder is poised up against a wall, and that ladder is exactly 5 meters long. You climb up to the top of that ladder, then unfortunately, because it wasn't well anchored at the bottom here, it's going to start to slip downwards. And it starts to slip downwards with a tip moving at 1 meters per second down. Our goal is to find the related rate, which is how quickly the bottom end of the ladder is sliding across the ground at some particular instant here when the ladder reaches 3 meters down. Again, it never hurts to have a few of the scenarios in mind. So we could have had the ladder being very upright, or we could have the ladder being even less upright, close to the bottom. In all those cases, we have the 5 meter ladder length. That doesn't change, and the ladder is always in contact with the wall, so we always have that 5 meter distance. And that leads us pretty naturally to define two distances, the distance between the wall and the bottom of the ladder, and the ground and the top of the ladder. Let's put those in words, just to be super clear. X is the distance from the wall to the bottom of the ladder, and y is equal to the distance from the ground to the top of the ladder. All right. Notice we can label those in every scenario here, and what we see quite quickly is we have a Pythagoras relationship going on here. What relationship is always true between these variables? Between these quantities? Well, it's always true that x squared plus y squared is going to equal 5 squared. All right. Now what do we want and what do we have? We know that dy dt, which is the rate at which the tip of the ladder is moving, is going to be 1 meter per second. And just being a little bit careful about that, if this ladder tip is moving downwards, then this length y is getting smaller and smaller and smaller. So be careful with your signs. Dy dt will be a negative 1 meters per second. What do we want? We want dx dt, which is how quickly the base of the ladder is moving outwards, or how quickly the distance x is changing over time. Perfect. We now have everything we need. We're going to take this relationship between the quantities, and then we're going to, going back a page, we're going to take that relationship with no rates and then apply implicit differentiation to get the rates that we know and the ones that we want in an equation together. We'll do that on the next page. This relationship ties x and y, which are both changing with time, together with this constant 5 squared. And so we can take the time derivative of both sides. One side is super easy, it's simply 0. The other side, we're taking the time derivative of x squared. We've seen this before, so I'll go a bit more efficiently here. And we have y with respect to t. The derivative of anything squared is 2 times the same thing. and then the derivative of the inside. What do we want here? We want dx dt. So we solve for that. Dx dt is going to be this brought over, negative 2y dy dt. Careful with our notation. And we still have the 2x. Or dx dt, bring the 2x over, negative 2y over 2x's dy dt. And the 2's cancel. Perfect. That's our general relationship between the rate at which the tip of the ladder is moving. And I'll call it a velocity here because it might have different signs. And this is the bottom of the ladder. Velocity. Going back to the question, we're asked to figure out this bottom velocity when the bottom of the ladder is 3 meters away from the wall. So notice the bottom of the ladder is away from the wall. That's exactly what x means. We can draw a little diagram to fill that up. When the base is 3 meters away from the wall, that's 4, and the y value isn't given in the question, but we can sort it out because 3 squared plus y squared equals 4 equals 5 squared. Let's get that hypotenuse correct. And so y squared is 25 minus 9. Y squared is 16, or y, it's only the positive root we're interested in here, is going to be 4. So at the moment where x is equal to 3, that told us that y was equal to 4. So dx dt, filling in all the blanks, is negative y over x, negative 4 over 3, times dy dt, which was negative 1 meters per second. And so we get positive 4/3. Natural units of x and t are meters and seconds, so meters per second. We would say then that the bottom of the ladder is moving away from the wall at roughly, well, exactly 4/3, but at 1.333 meters per second. Perfect. So another archetypal related rates problem where we have a relationship between the quantities, the two distances here, and that led us to, through differentiation, a relationship between how fast they were each changing over time, and then we could freeze frame at a particular instant and ask, at that instant, what's a particular rate and what's its value? Let's ask a slightly more refined question with a repeat of the calculations, but the rate at which the bottom of the ladder is sliding when the ladder is just about to hit the ground. So this tip is now moving down, so we actually have it close to here. You can try your intuition on this, or we're going to try it with calculations first, but think about it for a moment. What do you think is the velocity of this tip of the ladder here, or this base of the ladder here? Well, let's go back to the math. We have dx dt is negative y over x dy dt. This is fixed. And the case that we're interested in here is when y is equal to 0. That's when the ladder hits the ground. Well, if we put y equals 0 into here at that one instant, it doesn't even matter what x is, we're going to get 0. dx dt is going to be 0, or the bottom of the ladder does not move. Now that can either seem completely intuitive or completely counterintuitive. One way to imagine this, though, is to position yourself exactly at 5 meters away from the bottom here. Imagine yourself standing right at that point and asking what would happen to your toe if you were in exactly that position. Well, as the ladder moves down, it can never, ever reach past 5 meters. It's always going to get closer and closer to your foot, but it's never going to go past 5 meters. So when the tip hits the bottom, the distance will be exactly 5 meters, and the bottom is not going to move any further out. Well, that means its rate of change is going to be 0 at that instant. So there's an intuitive argument for why this is true, and it perfectly matches up with the results that we get from the calculation. So again, a very powerful combination of intuition and mathematical certainty